Hello guys, in this video we are going to discuss about the types of covalent bond, hybridization and shape of organic molecules, and finally representation of organic structure. So first we are going to start by discussing about types of covalent bonds. So basically we have two types of covalent bonds, that is sigma bond and pi bond. So we have sigma bond and second one is pi bond. Now if we go deep into details about these two types of sigma bond, we find that when we start with sigma bond, we'll find that sigma bond is a type of bond where the electron density is centered along the line connecting the nuclei forming the bond. So we have said that sigma bond is a type of bond where the electron density is centered along the line connecting the nuclei, forming the what? The bond. The sigma bond can be represented by the following structure. So that I'm going to draw the structures that represent the sigma bond. Let's say you have this nuclei of the s orbital. That one will result to that shape. It will result to that shape. Then on the s orbital, on the p orbital I mean, we'll have that structure that nearly resemble with the first structure that we had drawn, that they are slightly different to each other. So another point that we can add on this sigma bond is that sigma bond is formed by overlap of either s orbital or p orbital along the line between the nuclei. Sigma bond is formed by overlap of s or p orbital along the line between the nuclei, Then another point, we can say that all single bonds in organic compound are sigma bond. When you see a compound of organic that is single, it will thereby designated by a single bond. So all single bond in organic compound are designated by a sigma bond. All single bond in organic compounds are designated by sigma bond. In other words, single bonds in organic compounds that have single bond are examples of single bond. They have sigma bond. So the next type of covalent bond that we are going to discuss about is the pi bond. The pi bond, which can also be represented by this pi bond. So that is pi bond. So this pi bond, it is slightly different from the sigma bond, because this pi bond, it results from overlap between 2p orbitals oriented perpendicularly to line connecting the nuclei. Then from that point, it is only the pi bond is formed between overlap of 2p orbitals that are aligned perpendicularly to the line connecting the nuclei. Unlike the sigma bond, that we said that it is formed where the electron density is centered along the line connecting the nuclei. Here we have said that pi bond results from overlap between 2p orbital oriented perpendicularly to the line connecting the nuclei. So pi bond results from overlap between 2p orbitals oriented perpendicularly to the line connecting the nuclei. Another point that we can add on that is that the electron density is centered below and above the line connecting the nuclei. The electron density, in pi bond, the electron density is centered below and above the line connecting the nuclei. What is the effects of this issue where the electron density is centered below and above the line connecting nuclei? This makes the pi bond to be weaker compared to the sigma bond. Therefore, sigma bond is stronger than pi bond. So this point that we have mentioned here is what bringing the difference between the strength of those bonds. We find that sigma bond is stronger than pi bond due to the fact that the electron density of the pi bond is centered below and above the line connecting the nuclei. So when we draw the structure representing the pi bond, it indicates something like this. The diagram is shown by this. So this is positive, this is negative. It's gonna be positive, this is negative. It comprises of the dipoles that is going to result in this shape in this manner. So these are the electron densities. This is the line connecting the nuclei. So these are the electron density. The electron density is centered below and above the line connecting the nuclei. This is the line connecting the nuclei. So these are the electron density that are centered below this line, below and above this line connecting the nuclei. So on that few statements that we have illustrated, we are going to discuss more on the hybridization and shape. Hybridization and shape of organic molecules. So today we are just going to draw a table that indicates the type of bond, hybridization orbital, valence pair geometry, and angles subtended by the compound. So our subtopic is hybridization and shape of organic molecule. So here we are going to come up with a table. This table here, this column here is representing type of bond. Hybridization orbital, then geometry, then finally the last column here is the angle. So when we start with the type of bond, we start with the single bond. Single bond, the hybridization orbital is always sp3. Then the geometry is always tetrahedral. Like an example of those compounds comprising of single bond, we can talk of methane, ethane, the alkanes, the compounds that do have the single bond. Then the angle that they may subtend is subtended by single bond is 109.5 degrees. Then next we are going to discuss on the double bond. The double bond. Hybridization orbital is sp2. The valence pair geometry is trigonal planar or shape. The shape is trigonal planar. And angle form is 120 degrees. Then lastly, we are going to focus on triple bond. Triple bond, it's forming an sp. The shape it form a linear shape. And then finally the angle that it forms is 180. So On our next lecture, we will talk about more about the hybridization. But before we conclude, we are going to briefly discuss about the representation of organic structure. Representation of organic structures. So in representation of organic structures, there are several ways of representing organic structure. The first way is by using the Lewis form. So Lewis form. In Lewis form, this is where we represent the organic structure in a normal way. Let's say, for example, when we have ethane, we know very well that ethane has 2 carbon atoms. So we start by drawing those 2 carbon atoms surrounded by the what? By hydrogen. Hydrogen atom. So this is the Lewis form of representing organic structure. The next form of representing the organic structure is on condensed or Kenkule. Condensed or Kenkule, this is where carbon to hydrogen or carbon to carbon bonds are not shown in the structure, but carbon to carbon double bond and carbon to carbon triple bond are shown. For example, when we have propane is having 3 carbon atoms. So propane is having a structure of CH3, CH2, CH3. So that is the condensed structure of propane. What about butane when we are given a sample of butane? So butane, we know very well that butane has 4 carbon atoms. So we start by drawing the 4 carbon atoms. 1, 2, 3, 4. So we put the double bond here. We put the double bond here. That one means we'll put an hydrogen here, and then we put 3 hydrogen atoms here. Then we put 1 hydrogen atom here, and then we put another 3 hydrogen atoms here. So this is how the condensed structure of butane looks like. So where there is a double bond, we indicate. And also where there is a single bond, we also do indicate. So here, what is important to notice is this: carbon to hydrogen or carbon to carbon single bond are not shown, but carbon to carbon or carbon to carbon double bond or carbon to carbon triple bond are shown. So that is the difference that is there. So the last representation style is the skeletal or line angle. Here, neither carbon or hydrogen is indicated. The structure are represented using the line diagrams. So here we just use the line diagrams to represent the organic structure. So that is skeletal or line angles. Here we just use the line diagrams. For example, if you have this condensed structure of this molecule, H3, then there is a branch there. So here we are just going to count the number of carbon atoms in this structure. That is 1, 2, 3, 4, 5. And then where there is a branch, we indicate. So first of all, we must know where there is the parent chain. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the parent chain has the 5 carbon atoms. So we will begin by drawing those carbon atoms. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Those are the 5 carbon atoms. Then at the 1, 2, 3, 4, at the 4th carbon atom, there's a branch there of metal. So 1, 2, 3, 4, there's a branch there. So this is the skeletal structure representation of organic molecule. So from there, we have discussed what we were to discuss on hybridization and shape of organic molecule, structure and representation of organic structure, and basically the types of covalent bond, that is the sigma bond and the pi bond. So next time we shall discuss more on the hybridization, or how hybrid orbitals are formed in a given compound or molecule or atom. Let's say for example an sp2 hybridization. We'll be able to discuss more on the sp hybridization, sp2 hybridization, and sp3 hybridization. See you next time, guys, and kindly watch and subscribe and share this video.